Alright, so now we ask the question, well, how do we implement logical gates in quantum computing? The way we do it is by matrices. So we use matrix forms to denote classical and quantum gates. So a gate with n input bits and m output bits is represented by a 2 to the m by 2 to the m, 2 to the m by 2 to the n matrix. So a 2 to the m by 2 to the n matrix takes a 2 to the n by 1 matrix, and it outputs a 2 to the m by 1 matrix. Okay, so consider the NOT gate. NOT gate takes 1 bit input and it outputs again 1 bit information. So in other words, it takes cat 0 and it maps cat 0 to cat 1, and it maps cat 1 to cat 0. So in other words, it maps the vector 1, 0, this is the basis state cat 0, it maps 1, 0 to 0, 1, and it maps 0, 1 to 1, 0. So then we can define the matrix of NOT operation as 0, 1, 1, 0. So the ith column of this matrix represents the output of the function when given the ith basis vector in the inputs. So this is the output of NOT when given the basis state 0, and this is the output of NOT. The second column is the output of NOT function when given the input cat 1. This is the first basis state, and this is the second basis state. Okay. And what about the other matrices? So what about the logical gate AND, NAND, OR, NOR, and XOR? So these are represented by 2 by 4 matrices. So AND, it takes a 2 qubit matrix and it outputs a 1 qubit information. So on input 0, 0, it outputs cat 0, right? So AND of 0, 0 is 0. So cat 0 is basically 1, 0. On input 0, 1, it outputs again 1, 0. Third column is 1, 0. And on input 1, 1, it outputs cat 1. Right? So these are the inputs, and the output is the corresponding columns. And NAND is basically taking AND and taking the NOT. And it's 0, 1, 0, 1, 0, 1, 1, 0. It's simply the NOT of this matrix. Similarly, OR is 1, 0, 0, 1, 0, 1, and 0, 1. NOR is the negation of this matrix, so it's 0, 1, 1, 0, 1, 0, 1, 0. Exclusive OR, that's bitwise addition modulo 2. It's 1, 0, 0, 1, 0, 1, 1, 0. Okay, so quantum computation is mostly relied on reversible computation. And in fact, in the beginning, most of the studies about quantum computing were associated with study of reversible computation, because quantum computing, the all computations have to be reversible. This is because we are restricting our attention to closed quantum systems. So that's why we have the reversibility condition. At any time, at any stage, we could reverse the computation and obtain our original input. So we say that a computation is reversible if the input can be uniquely recovered from the output. The NOT gate, the NOT operation, is reversible, clearly, because from the given output we can uniquely recover the input. If the output is 0, then the input must be 1, right, and vice versa. But there are also non-reversible gates, such as AND or NOR, right? So we lose information here. Well, given the output 1, so if AND of xy equals 0, then from this given output we cannot uniquely recover what x and y are. Well, x could be 0, y could be 1. Or x could be 1, y could be 0. Or both of them could be 0. Well, we might not know which one the original input is. Okay, so we lose information here. But this reversibility requirement, fortunately, does not put any limitation on what we can compute. It wasn't really clear back in the 1970s if we could compute anything classically, that we could compute it quantumly. But it became clear later on that we could actually compute any classical computation reversibly, okay? Hence quantumly. So every step of a computation must dissipate some amount of energy, okay? But this energy is not because of production of information, but it's due to losing information. Okay, so we actually dissipate energy during the computation, not because we produce it, but because we lose some information. And this came to known as Landauer's principle. And roughly, it could be described as energy dissipation is not due to the production of information, but is due to loss of information. Okay, so now fortunately it was shown later that any classical computation can be done in a reversible manner. So this shows that in principle, in theory, no energy or no heat would be produced in classical computation. We could do our computations without dissipating energy in principle. So any non-reversible logic gate can be transformed into a reversible gate, okay, computing the same function. And we will introduce a special kind of gate called Toffoli gate later on. So I will explain about that more in the upcoming lectures. So we want our quantum gates to be reversible. Okay, all of our quantum computations must be reversible. And what's more is that we do not want any junk information to be produced in the output. Now, what do I mean by that? Well, consider the function, for instance. So we have x, y, z, okay, x, y, z, x or xy. Okay, so now suppose that z is 0. Now what does that compute? Now apparently f computes xy, right? Because 0x or xy equals xy, right? So this is the out. So this computes end. So this is the output of then the end function. But then these two bits are junk, right? There's no need to produce these. So we do not want any junk information in the output, and the reason will become clear in a moment. So given a classical function f, we want to define it quantumly. Okay, we want f to be reversible, and the output should not contain any junk bits, any junk information. At any stage of the computation, we should be able to recover the computation and compute the inverse function at any stage. Okay. Now, okay, so, but as I said, end function, or function, or other logical gates, except not, are not reversible, right? I mean, function end contains two inputs and one output. Well, in order a function to be reversible, the number of inputs should be equal to the number of outputs. Okay, so so how do we transform a non-reversible function into reversible counterparts? Well, for this we need to introduce auxiliary input wires and output wires. Okay, as in this case, there are equal number of output and input wires. So first we need to add auxiliary wires in the input and in the output. Okay, so we need to preserve the number of wires and number of wires in the input and the output, and then we obtain a reversible version of the given irreversible function. So what we do is that when adding auxiliary wires, we may produce junk bits, and these junk bits may prevent interference in quantum computing. So why is that? And by the way, can't we ignore these junk bits? And what's the problem of having junk bits? So the problem is that it prevents interference in some cases. Okay, having a junk bit or not, sometimes it affects whether we're going to have an interference or not in the computation. So let me demonstrate this. Let me give an example. So suppose that we start with, okay, so we do not want junk bits to be produced in the output because it may prevent interference. It may prevent interference because the output bits may be entangled with the junk bits. So let's consider, let's assume that we start with states say x1 plus x2. Okay, and let me ignore the amplitudes for simplicity. And let's consider the function x 3-qubit function x 0 0, and it outputs x, and this is the output of the function f of x, and some junk bits in the third qubit. Now if we apply this function, okay, on a superposition, let's apply this on a superposition x1 plus x2, and the output will be, in this case, so by linearity we have x1, we have f of x1, we have junk bits associated with x1, plus we have x2, f of x2, and junk bits associated to x2. Alright, so now let's apply the following transformation. And there are some similar transformations in quantum computing. We will see these when we talk about quantum gates. So let's apply the following transformation. It maps x1, ket x1, to x1 plus x2, okay? And it maps x2 to x1 minus x2. All right. So now substituting these two into this superposition, we get x1 maps to x1 plus x2, and then we have f of x1, and then we have junk of x1, plus we have x1 minus x2, and then we have f of x2 and junk of x2. Alright, so let's analyze this. Now, if f of x1 is equal to f of x2, and if junk bits of x1, so junk bits produced when given the input x1, is equal to jx2, then what happens? Well, then x2 will completely cancel out, right? So the state will interfere with the other. Then we have an interference, right? x2 will completely cancel out. Okay, but what if it were the case that f of x1 equals f of x2, but the junk bits were not equal to each other? So if f of x1 equals f of x2, okay, but not, okay, let's say, but j of x1 is not equal to j of x2, then in that case there will be no interference. there would be no interference. But there would be interference if we could get rid of the junk bits. So having extra junk bit makes a difference between not having it. Okay, so that's why we don't want any junk information generated in the output. But there's an easy way to avoid this situation. What we do is that we copy the output, okay, f of x, and then we run the circuit backwards. So there's a general scheme of a reversible circuit for quantum computation, and this is how it works. So suppose that we have a classical function. Suppose f is a classical non-reversible function. Classical non-reversible function. Okay, so we want to implement this quantumly. Implement f quantumly. Alright, so how are we going to do that? Well, first let's take the classical reversible version of f. Okay, so let's call it CF. This is the classical reversible version of f, and it might generate junk bits. Okay, so CF, okay, the classical reversible version of f, not necessarily compatible with quantum computing. But suppose that we have inputs and some additional auxiliary input wires. Okay, maybe this is the output wire, this is the workplace wire, okay. And we have x, we have f of x, and we have some junk bits, okay. Alright, so now what we do is that we run the circuit backwards. So CF inverse, and then we get x 0 0. So okay, so in this way we got rid of the junk bits, but we also got rid of the output f of x. So what we do instead is that we copy f of x here. So we take this C naught of f of x and 0, okay, copy wire, and the input is 0. And we take the C naught of 0 and f of x, and we carry the wire here and obtain the output. So this is the general scheme for implementing the function f quantumly. It's reversible, and we got rid of the junk bits. So all quantum circuits will be in this form, okay? But of course, we're not concerned with the internal workings. Alright, so in the next lecture we will talk about more reversible gates, and we will introduce some quantum gates. So I'll see you in the next lecture.